Welcome friends and welcome to my series of video lectures on design of RCC structures. We are in chapter 2, flexural analysis and design of singly reinforced rectangular beams. This is video lecture RCC 2.7, problems on balanced flexural design. For best video quality, watch this video on laptop or desktop with resolution set to 1080p, that is HD. Learning outcome expected from this video is to perform balanced flexural design of beams. The contents of this video lecture are 1. Types of problems. 2nd. Numerical problem 2.7.1. 3rd. Numerical problem 2.7.2. We are going to use some key terms in this lecture: design, moment of resistance, load carrying capacity, balance section, ultimate load. We have our best friend Smarty with some studying tips. Write down your own notes while watching this video. Pause or rewind the video whenever required. Do solve the formative and summative assessment quizzes given at the end of the quiz. Friends, in this video lecture, we are going to solve two numerical problems on balanced flexural design of beams. But before we proceed for the problems, let us have a quick review of the types of problems. There are two types of problems. One is analysis type problems and second, design type problems. The analysis types of problems are having size of the beam as the data, that is B, D and AST. And what is expected from this size of beam is the actual strength of the beam. The actual strength of the beam is expressed in terms of ultimate moment of resistance MUR or the ultimate load carrying capacity WU. So this is the type of problem which we call as analysis type of problem. The design of type of problem is exactly reverse of the analysis type of problem. Here the expected strength is given, that is the maximum bending moment the beam is supposed to resist, MU max, that is calculated or that is given, and from this we have to decide the size of the beam. That means we have to decide the breadth, the depth of the cross section and also the area of steel in the cross section. So these are basically the two types of problems. Now, while solving the analysis problem, we have to follow three steps. First is calculate the value of XU. This is depth of neutral axis, and check whether the beam is under reinforced or not. Accordingly, you have to take some steps that we have already done in the earlier video. Then the next step is calculate ultimate moment of resistance, and the last step is, if required, convert this MUR into the load carrying capacity. So this is briefly the procedure of solving the analysis types of problems. Now the design problems are divided further into two parts. We can have either a balanced design or a balanced section designed or an under reinforced section design. We know that the RCC sections are classified as balanced, under reinforced or over reinforced sections depending upon the relative quantities of steel and concrete. IS 456 is not allowing us to design over reinforced sections. We have taken a detailed study of all these things in the earlier video. This is just a review. So we are aware that over reinforced sections are not to be considered. That is why the design problem consists of either balanced section design or under reinforced section design. Now when the design of balanced section is considered, we have to use what we call as design constants. The detailed explanation of design constants has already been covered in the earlier videos. So we recollect here that there are four design constants, and using their values we can directly find out the design conclusions for balanced section. So we have to use design constants. We have to calculate B and D using the design constants QUB, and we have to calculate the ASTB, that is balanced area of steel, using the design constant PUB. Now, if the design is under reinforced design, in that case, we have to assume some values of B and D, breadth and effective depth of the section. Then accordingly, we have to use a separate formula for AST, and we have to calculate AST under reinforced. So, this was a brief revision of the various types of problems, the two types of problems that we get in the flexural study of the rectangular beams. So friends, with a brief review of types of problems, we now proceed for the problem on balanced flexural design. This is problem 2.7.1. Let us read the statement of the problem. A simply supported rectangular RCC beam has effective span of 6 meters and it carries a total working load of 50 kilonewton per meter. Design the beam as a balanced section assuming materials of grade M20 Fe415. So this is a problem on simply supported beam. Let us have a look at this picture, which is a common picture of simply supported beams. You can see these three beams at this level supported on columns. We can treat these beams as three simply supported beams. Similarly, there are three more beams at the upper level. So this is a common picture. This gives us a reference of the site or the field while solving the problem. Now let us start solving the problem. Solution. Let us first draw the diagram from the statement of the problem, and then we will interpret the statement of the problem by reading the statement again step by step. When we read the statement of the problem, the important point we come across is we are asked to design the beam as a balanced section. So this problem is of design type. Second thing, the design is supposed to be balanced type and not under reinforced type. Now the third thing is beam type is given to be a simply supported beam. So the statement starts with this point, that simply supported rectangular beam. Whenever we get this information that it's a simply supported beam, it further gives us two more bits of information. One, that for a simply supported beam, the type of bending will be sagging. Now due to sagging bending, we will have tension zone at the bottom. So here in this diagram we can see that this is a simply supported beam carrying UDL, uniformly distributed load, and simply supported on two columns here. Now the beam is divided in bending, the beam is divided into two zones, compression zone and tension zone. When the beam is simply supported, the tension zone is at the bottom and compression zone is at the top. The two zones are separated by a neutral layer. The same neutral layer gets intersected in the cross section and it is called as neutral axis, NA. Now we see that the bending moment diagram of the beam is a parabolic curve with the highest value of bending moment at the center of the beam for this uniformly distributed load. So this point at which the bending moment is maximum, this point or this cross section will be called as critical section. Critical because the value of bending moment is maximum or highest at that point. So we take the cross section AA as critical section AA here, and we show the details in cross section. Here we see width B, then the effective depth small d, and the AST as the bars of reinforcement. We know that there is tension zone at the bottom and therefore we are providing the steel reinforcement at the bottom. Now we don't know how many bars we will require, so we are just showing as a sample 3 bars here. So if we see further, the critical section for flexure is midspan. The span of the beam given is L. Working load W is 50 kilonewton per meter. We have to note that it is working load and not ultimate load. Now the materials of grade M20 concrete and Fe415 steel are provided. Now this further supplies us the information that the design constants There are two design constants required for the problem of balance design. For M20 FE415 grade, here is the entire table. From this table we can get these values. We require QUB, the moment of resistance constant, and its value is 2.76, and the second is PUB, the steel constant, so its value is 0.96. So as we know, we have to remember the values of this table readily, so that we are not required to spend extra time in calculating them while solving the problem. Now this is all the data that we have. We are supposed to find out three things. It is a balanced design. We know that to design a beam means to find out or to decide its dimensions, its cross-sectional area, as well as the amount of steel we want to use in it. Now since this is a balanced design, we will be using the suffix B to the symbols. So we want B, DB, balance depth, and ASTB, the area of steel for balance section. So here B is not known, D is not known, and ASTB is not known. Now we will proceed for step 1. First step. First of all, we will have, while designing the beam, we will have to first find out what is the maximum bending moment the beam is supposed to resist. So calculation of MU max. MU max means maximum ultimate bending moment the beam is supposed to resist. Now the data is given. So for simply supported beam, the maximum ultimate bending moment MU max is given by the formula WU L square by 8 as shown here. So we will put the values, but before we put the values, we find here that we want the value of WU. WU, the suffix U stands for ultimate. Now in the beginning we have noted that we have been given the value of working load W. So we will have to convert this W into WU by multiplying that W by the load factor or gamma F, which is partial safety factor for load. We know that we can recollect that in limit state method which we are using for this subject, we have to increase the values of load by the factor, load factor, and then that value we have to take for our calculations. So here working load is given as W equal to 50 kilonewton per meter. Hence ultimate load WU will be gamma F into W, that is 1.5. The value of gamma F is taken as 1.5 according to IS 456-2000 into 50. So this will give us 75 kilonewton per meter. So after having converted this W into WU, we can use this formula WU L square by 8 here, and we can put the value as 75 into 6 is the span square upon 8, and this finally amounts to the ultimate maximum bending moment MU max as 337.5 kilonewton meter. So that was step 1 of this problem. We will continue in the next slide. In continuation of the problem, we will now proceed for step 2. The step 1 has given us maximum ultimate bending moment value MU max as 337.5 kilonewton meter, and this is the data that we have got. Now we will proceed for step 2. We want to design the beam, means as we said earlier, we have to find out the cross-sectional dimensions and we have to find out the area of steel. So in step 2, we will calculate the values of B, that is the breadth, and D balance, that is the depth for balance section. Given that the beam is balanced. Now the method of getting the value of B and D for a balanced section is to use the design constants that we have already taken down at the beginning. So hence we will use the formula MUR balanced equal to QUB into BD square. This formula we have to use for calculation of B and D, and this we will equate to MU max. So calculation of B and D will be done by equating MUR to MU max. The ultimate moment of resistance of the beam will be equated to the highest maximum possible bending moment to which the beam is subjected. Now, here we find there are two unknowns B and D in the equation. So one unknown will have to be assumed. Value of one unknown will have to be assumed. So we will usually assume the value of B, that is breadth of the beam, and we will usually take it as 230 mm. There is a practical significance to this value of 230 mm. The significance is that 230 mm happens to be the thickness of a 1 brick thick wall. So this becomes the wall thickness. We know that the beams are usually supporting the walls, and beams are coming under the walls also, and that is why if their thicknesses are unequal, then there is a projection of beam outside the wall and or a wall outside the beam and so on. So these offsets are architecturally a problem. That is why we will, as far as possible, try to avoid the offsets of beams from outside the walls. So to make up these widths, we will have the width of beam B as 230 mm, which is usually the wall thickness. Of course, when the value of B is given in a problem as different than 230, you have no choice and you have to take that value and solve the problem. Now, we will put this value 230 and in this equation, and we will just substitute the values in this equation. So we have got MUR equal to QUB into BD square. So this MUR is 337. This is already taken from step 1. We will multiply it by 10 raised to 6 to convert it into Newton and mm, because on the right hand side we are going to use the values in Newton and mm. We know this QUB, design constant, whose value is 2.76, its unit is Newton per mm square, whereas this value of bending moment was in kilonewton meter. So we have to be, of course, aware of the units, and accordingly we have to make numerical adjustments. So this is 230 into d square, and now here we come across the solution of this first part of the problem, that we get this value of dB, and this is the value we get as the depth of the beam, balance depth of the beam. So this is the first part of the problem, that we calculate B and D, both of them, and we get this value. Now we proceed for the next step, step 3. Step 3 is about calculation of area of steel required. We have calculated the values of B and D here, and the next step is calculation of area of steel. That will end the problem. So this was the value of B as shown in this diagram, and this was the value of small d as shown here. Now we are left with calculation of ASTP. So since the beam is a balanced beam, again we will be using a design constant. Now design constant which is appropriate for AST is the constant PUB, which is the steel constant, and that is why we will use the formula ASTB equal to PUB into BD. This is the formula. So here we will recollect from the earlier slide that the value of PUB is 0.96%, and we will use that value. So this is 0.96 upon 100 into 230 into the effective depth which we have calculated from the earlier step 2. So here, like this, we substitute the three values and we get the area of steel like this. So this is the value of area of steel. B means balanced steel. So this is the value of area of steel, and that is the last thing we wanted to calculate from this problem. So now here we see the section with its dimensions as well as the area of steel, and this is a balanced section. So we get this balanced beam design for the complete data that was given to us. So we can put our answer in a nutshell. So the answers are B, breadth of beam as this, the depth of the beam as this, and this is the area of steel that we have calculated. So these are the answers of the problem. So in this way we have solved problem 2.7.1, in which we have designed a simply supported beam carrying uniformly distributed load as a balanced beam. Now there can be some variations in this problem. Small variations can occur in the data and the procedure of solution of the problem. So instead of solving completely new problems like this, if we just understand the variations that can be possible in the problem, we can understand how can we solve the other problems also. There are two possible variations. One is the loads can be other than the UDLs. This is a UDL, uniformly distributed load. In the data they can give any type of load. You know that you can get a coupled load, or you can get a concentrated load, or you may get this uniformly distributed load over a part of the beam also. So this was a simple case in which the uniformly distributed load was given and was acting over the entire span. So if you get any different loads, method of calculation of mu max will be accordingly modified. So you will have to use some standard formulae, some other standard formulae, and you will have to finally add up the bending moments to all the types of loads, and that will give you the value of mu max. Sometimes your loads may not fit into some standard cases. So in that case you will not get standard formulae like WL square by 8, WL square by 2 and so on. In that case you will have to rely on the first principles of finding out bending moment diagrams as discussed in the subject of structural mechanics. So that was the first type of variation that we can get. And second type of variation is, as we have assumed this B as 230 mm as wall thickness because nothing was mentioned about the value of B. In some cases they may provide us some relation between the values of B and D. For example, depth may be twice the breadth. That may be one relation. Or they may be saying that D is to 3/4 of B and so on. Or they may be giving you directly the value of B as say 300 mm, whatever. Or they may sometimes give you the entire cross section also, B and D both. In that case, that step 2 is already over. You have to directly switch to step 3 and calculate simply the area of steel. So in case the values are not given, we are assuming the values with some logic. But if the values are given, obviously we will have to take the values as they are given. So this was the problem 2.7.1, and now we will proceed for the next problem, in which we will discover some new details of the same type of design problem. Friends, now we will be solving one more problem on balanced flexural design of rectangular beams. Problem 2.7.2. Let us read the statement of the problem. A rectangular RCC beam has effective cross section as 230 mm by 450 mm. Calculate area of reinforcement for the beam as a balance section. Also calculate working load carrying capacity of the beam for a simply supported span of 5 meters. Assume materials of grade M25 Fe500. Again, here we get the example of the beam as a field example, that here this is a construction site going on and we are having 3 beams on one level and 3 beams at the other level. There are columns and we can assume all these 6 beams to be simply supported over the columns. Now we proceed for the solution of the problem. We start as usual with the diagram and interpretation of the data. Now this problem, the data is given in somewhat different form, that's all. If we read the problem statement carefully, we find that the cross section of the beam is already given. The effective cross section is already given, but the area of steel is not given. So this we can call as a partial design problem. Total design is not expected. because total design involves cross-sectional size as well as area of steel. Here cross-sectional size is given but area of steel is asked. So we will call this problem as a design type problem plus analysis type problem, because the analysis part of this problem comes at the end of the statement. Calculate working load carrying capacity of the beam. That is what they have asked. So we can say that this problem is a mixture of design type and analysis type. So in design type we are getting partly data given as the cross section is given, but the second part is not given, whereas the analysis part is following the design part because they want us to calculate the value of load carrying capacity. So this analysis and interpretation of the statement of the problem will make the action clear about the solution of the problem. So we classify this problem type as design type plus analysis type problem. Now the data is balanced design. Since there is a part of design in the problem, we have to first of all ask whether it is a balanced design or under reinforced design. So it is given clearly that as a balanced section. So we have to take the clue that this is a balanced design problem. Now obviously there is a beam, so beam type and everything comes. So the beam, it is given as simply supported. Here they have mentioned at the end simply supported span of 5 meters. So it is a simply supported beam of 5 meters span. Now again, when the beam is of simply supported type, it is having sagging bending, so it is having tension zone at the bottom and compression zone at the top. And the critical section for flexure, when you are having only uniformly distributed load over the entire span, the mid-span section, the middle section along the length of the beam or span of the beam is the critical section for bending moment. That is, the value of bending moment is maximum at that point, and it is WUL square by 8. So breadth of the beam is given, 230 mm is given, 450 mm effective depth is also given. We are only supposed to calculate AST balance. So this is a part of the problem of design. So the design constants will be required. We can see that the materials are M25 and Fe500 grade. And we know that the design is a balanced design. So when there is a balanced design, we directly use the values of design constants. The values of design constants directly depend upon the material grades which we are using. So data tells us that material M25 and Fe500, these two materials are used. So for that, according to this reference table, we get the values of QUB as 3.34 Newton per mm square and PUB at 0.95% as the steel constant. So we are now supposed to find out ASTB, balanced area of steel, and the working load carrying capacity W. So step 1 of the problem takes us to calculation of balanced area of steel. In the earlier problem, step 1 was finding out B as well as D, but that part is not required here because it is readily given. So given that the section should be balanced, we will be using design constants. Now for calculation of ASTB, we will be using the design constants PUB. Here B stands for balance section. So ASTB is PUB into BD. This formula we have already derived in the earlier video. So we put the values 0.95%. So this comes 0.95 upon 100 into 230 into 450. So this gives us 983.25 mm square. So this is the area of steel required for this beam and to make it a balanced beam. So this is the first part of the answer. Now we proceed for the next step. In the next step, they are asking also calculate working load carrying capacity. The calculate area of reinforcement that we have got. Now the second thing, we want to find out working load carrying capacity W. Now we know that whenever we want to calculate working load or the ultimate load or load carrying capacity, we are equating the maximum bending moment to ultimate moment of resistance. So that equation comes in the beginning of step 2. Mu max equal to MUR balanced. So this is equal to, we get the values WU L square by 8. This is the value of Mu max. You can see here in the bending moment diagram. So, and this will be equated to MUR balanced. This is QUB into BD square. So the right hand side is the side of resistance generated by the beam, and left hand side is the side of the action developed by the loads, that is the maximum bending moment. So by equating the two, we are going to get the value of ultimate load. So just put the values here. WU into 5 square, span of the beam is 5 meters, upon 8 equal to 3.34 is QUB, design constant. Then B and D into 10 raised to minus 6 is the factor which is the adjustment for units, kilonewton meter to Newton millimeter, and vice versa. So this calculation finally gives us the value of WU, or the ultimate load carrying capacity, as 49.78 kilonewton per meter. Now they have not asked us the value of ultimate load carrying capacity. They have asked us working load carrying capacity. That is why we have to be very faithful and very clear about every word of the problem statement. So if they are saying working load carrying capacity, this ultimate load carrying capacity will have to be converted into working load carrying capacity by a small formula. So working load carrying capacity will be W equal to WU upon gamma F. Gamma is F is partial safety factor for load. So we get this 49.78, this value divided by the load factor 1.5, and this amounts to 33.19 kilonewton per meter. So this is the working load carrying capacity. So this WU, as we see in this diagram, this would be 49.78, and here the value of W would be 33.19. So in this way we get the second answer of the problem also. So we can finally put the values of the answers like this: ASTB and W. These are the two values of answers we get. So friends, that was problem 2.7.2 on the balanced flexural design of rectangular beams. So friends, before we conclude this lecture, we will have an formative evaluation self-test. So pause the video and write on a paper the following question: design a balanced rectangular simply supported beam to resist an ultimate bending moment of 110 kilonewton meter, assuming materials of grade M25 Fe500. Take D equal to twice B. This is an analysis level problem. So do solve this problem, and then we will proceed for the last slide. So friends, now is the time to sum up. This was lecture 2.7, problems on balanced flexural design. The expected learning outcome from this video lecture was to perform balanced flexural design of beams. The contents of this video lecture were: 1. Types of problems. 2. Two numerical problems, 2.7.1 and 2.7.2. We used some key terms in this lecture: design, moment of resistance, load carrying capacity, balance section, ultimate load. Contact your teacher if you have any doubts or queries. At the end of the lecture, in the YouTube version of this video lecture, in the description section, the link for the Google quiz will be given. So do attempt that online summative quiz, summative assessment quiz provided by me. Now at the end, here is Smarty back with us to say us thanks. So thanks a lot for watching this video. Have a nice time and goodbye till we meet again.